Hey there, Adrian Rosebrock here from PyImageSearch.com, and today we're going to have a brief introduction to the TensorFlow Data API. Now, I really love the TensorFlow Data API because it allows you to supercharge your data processing pipelines. So if you have any experience working with TensorFlow and Keras, then you know that in order to process large data sets that can't fit in memory, you typically use the image data generator class. So this class is responsible for loading batches of images from disk, and then it maybe applies data augmentation or data scaling as well. And if you've compared the image data generator performance to other libraries, specifically such as PyTorch, then you know that the image data generator is quite slow. It's not as fast as what some of the other deep learning pipelines have been able to build. So TensorFlow in version 2 has started to create this like almost convergence. Like it's almost like PyTorch and TensorFlow are starting to converge together in their API styles, specifically regarding how they handle data sets. So you can subclass this dataset class, and you can add in these different methods that allow you to load data in batches, and then that data is then returned to the model for training. So a funny story. When I was in middle school, entering high school, this was about the time when popular like car movies like Fast and Furious and Gone in 60 Seconds were becoming popular. And Gone in 60 Seconds in particular with Nicolas Cage. That movie always just like I always thought that movie was so cool as like a 12, 13-year-old kid and be like, "Man, I want to go steal some cars and I want to drive super fast, but I'm going to do it for these altruistic reasons." And I don't know. I just love that movie. One of my favorite scenes and one of the most famous scenes from the movie is when Nicolas Cage like gets this Ford Mustang, this Shelby GT 500, and has a nitrous oxide tank in it. So he like flips the switch in the car and he presses the nitrous button, and the car just like boom, like takes off like crazy down the road. And that's kind of what using the TensorFlow Data API is like. If you've been using this image data generator, then you've been driving like a super slow like 1991 Honda Civic with a flat tire. But if you upgrade to the TensorFlow Data API, well, then you're going to have just like cans of like nitrous oxide in the trunk of the car, and then all you gotta do is press the nitrous button, arm it, and press the button, and boom, you take off. So that's what we're going to be discussing here today. We're going to get this introduction to the TensorFlow Data API. We're going to understand how it works, and then we're going to benchmark it and compare it to the image data generator class. From there, in next week's tutorial, you're going to learn how to use the TensorFlow Data API to actually train a neural network. So again, today this is just an introduction. Let's learn the basics. Let's do some benchmarking. Next week, we'll take that TensorFlow Data API and then plug that into a neural network. And the final tutorial in this series will discuss data augmentation within the TensorFlow Data API. So as a high-level overview of what the TensorFlow Data API gives us, is it gives us the ability to take any number of data sets. So this could just be like raw NumPy arrays, could be like a CSV file, the TensorFlow record file format, plain text data, image data, audio, like whatever you have, wherever it's stored, whether it be on disk, on a network attached storage, whether living in the Google Cloud or other clouds. So that's where your data lives, and that constitutes a data set. Now, what TensorFlow Data API allows us to do is write functions that connect to wherever this data is stored, pull it out, and then create an instance of a TensorFlow Data class. Now, that is where the magic happens because that allows us to start yielding instances of data to our TensorFlow model so that it can be trained. Under the hood, the TensorFlow Data API is doing all sorts of things like extracting the data from the raw data set itself. It's applying any transforms to the data, such as data augmentation or scaling, and then it's passing it on to the model. But what's really nice is that this data API is optimized. So there's been a lot of effort from the TensorFlow developers such that we can run multiprocessing and multi-threading underneath the API itself. And the benefit there is that your model is never waiting for data such that it can be trained. That data is always available thanks to these optimizations that the TensorFlow Data API has done. Because when you're training a model, it is a traditional producer and consumer relationship. So the TensorFlow Data API, that's our producer. This TensorFlow Data API is responsible for building this cheeseburger. And our consumer, the neural network, wants to eat as many cheeseburgers as it possibly can. So the producer has to work super, super hard to feed the consumer. And the more data that's available, or the more cheeseburgers that the producer has stockpiled, then the happier the neural network is going to be. So that as soon as it's hungry for more data, you can just reach over, grab that cheeseburger, and continue eating data, learning new patterns, and just becoming a better model. So that's kind of the gist of what the TensorFlow Data API is. Let's start discussing how we can actually build such a data pipeline and what it looks like. So I have a project directory structure pulled up over here, and we have two Python scripts. One reading from memory, that's going to discuss building a TensorFlow Data API for a data set that can fit entirely into the main memory of your machine. And then we're going to learn how to work with data that's residing on disk, meaning maybe the data set's too large to fit into memory, or just due to how the data is fragmented, you can't keep it all in memory at once. We then have this little helper function here. This is going to allow us to benchmark how long the image data generator takes compared to the TensorFlow Data API. And this is the data set we're going to be working with for the reading from disk Python script. This fruits data set comes from Kaggle. It has, let's see, looks like 7 classes. The goal of this data set would be form classification. So like within the Apple subdirectory, you have examples of apples. And for broccoli, examples of broccoli images and so forth. So if we were going to build like a classification model, you would connect the TensorFlow Data API to this directory here, and then that would parse the data out and then send that over to the neural network to be trained. But we're not going to get there yet. We just want to understand the performance increases that we're going to be getting from using the TensorFlow Data API as opposed to the image data generator. So let's pop open to PyCharm here. And as you can see, I have our project directory structure loaded up. And let's start with this helpers function. And inside this file, we have a single function benchmark. And we're going to take an instance of a data generator. That data generator could be the image data generator class from Keras, or it could be the TensorFlow Data API instance. It's going to be one of the two. And the number of steps here, that's the number of steps we're going to take in generating data from this data set. So almost as if we were batching data. So if we wanted to train a neural network for 1,000 steps, well, that's 1,000 batches of data. And we want to know how long it's going to take for each of these classes to generate 1,000 batches of data. So what we do is we start our timer, we loop over the number of steps we want to take, and then we call the next function, which advances the iterator of the data generator and then gives us back our data back. We then stop the timer and then return the difference between the ending and starting times. That's going to tell us how long that data set generation process took. Let's put this function to work, and we'll go to reading from memory. And we start off by importing our little benchmark function. We're also going to import the image data generator class. If you haven't used this class before, if you want some additional experience on it, what I would recommend you do is go to the PyImageSearch blog, and you could search for image data generator. There are so many tutorials here that I've authored on image data generation, but the one that you should read here is data augmentation with image data generator. It explains how the class works, and it also explains like what data augmentation is versus isn't, because there is a bit of confusion about the different types of data augmentation techniques. So that tutorial will get you up to speed. Now, again, we're working with a data set that's going to fit into memory. So we're going to use the Cipher 100 data set. And then we come to this really, really important import, the auto-tune parameter from the TensorFlow.data submodule. As I've already mentioned, within TensorFlow.data, like this is where all of our optimizations are taking place. The TensorFlow developers have just taken excruciating care to ensure the data generation process is as fast as possible. So when we pass this auto-tune parameter into the tf.data API, it's going to tell TensorFlow to go under the hood, to look at our CPU, to look at how fast it is, look at our RAM allocation, and figure out, all right, how much data can I generate in cache for this neural network such that our producer-consumer relationship is sufficiently satisfied and will enable us to train our neural network as fast as possible. So that's what this auto-tune parameter has done. It's super important. It tells TensorFlow to perform all those underlying optimizations. And then here, of course, is our TensorFlow library itself. So in order to benchmark image data generator versus the tf.data API, we're going to generate data of batch size 64, and we're going to generate 5,000 steps of data. So what that means is that if you open up a Python shell, you'll see that 64 times 5,000 is about 320,000 instances. So we're going to generate 320,000 instances from the Cipher 10 dataset. So let's see how we do that. We start off by loading our training and testing set using Keris's Cipher 100 load data helper function. And then let's create our image data generator. So here we create an instance of the original image data generator from Keris. And we're going to say, let's generate data using the training set of batch size 64. And then we're going to shuffle that data such that it's returned in randomized order. So this is the traditional approach to applying image data generation with Keris. You could apply any other types of data augmentation in here as well. So that's where you would do your random resizing and your scaling and your horizontal and vertical flipping and whatever else. Additionally, this class contains the flow from directory function. So if your data set's too large to fit from disk, you would call flow from directory to read batches of data from your directory and then return that to your neural network. But for this, since all the data fits into memory, we just need to call the simple flow function on it. Now we need to compare the performance of image data generator to our tf.data API. So this is how you create an instance of a dataset class in TensorFlow. Typically, what you'll do is call the from tensor slices function, and you're going to pass in an array of something. In this case, that something is our training data. It's the images and the class labels. Now, if your data set was too large to fit into disk or in memory, as we'll see, then you would just pass in the image file paths, and you would define a function to take that file path and load the image and do any pre-processing to it. But since our data already fits into RAM, all we got to do is pass in the raw images themselves and then the class labels. Now here is the real magic of the TensorFlow Data API. And anytime you use the TensorFlow Data API, you're going to create something like this. It's a pipeline of sequentially called functions. So the first parameter is the dataset instance, and then you're going to call shuffle on it, and you're going to pass in a parameter. So this parameter call is essentially a buffer size. We want to buffer 1024 images from our training set. And we want to randomize the order of those 1024 images in our buffer. And I'll explain a little bit more about how that buffer is populated in a second. But initially, on the first call of this data set, it's going to look into TrainX. It's going to build an initial buffer of 1024 images, and then inside that buffer, then you're going to randomly shuffle it. Caching is also important because underlying the TensorFlow Data API, TensorFlow can actually do caching, which will speed up the actual process of generating data. So the cache method is something you're going to be calling often. The repeat method is also super important, and what it actually does isn't necessarily intuitive based off of the name of the function. So what's going to happen when we're training a neural network using this data set? Well, we know how a neural network works. It works in epochs. So for each epoch, we're going to loop over the entire training set, and then in batches, we're going to update the weights to our neural network. But what happens when we reach the end of an epoch? Does that mean that TensorFlow knows to go back to the beginning, start a new epoch, and then work its way through the data? Well, no, not necessarily. And that's what this repeat method says. It says once you've reached the end, once you've exhausted all data in the data set, calling repeat is going to tell TensorFlow to go back up to the top, back to the beginning, and start working its way back through it. Here, the batch function tells TensorFlow to yield data in batches of whatever parameter you pass in here, which in this case is 64. So we want to yield batches of data of size 64. So that's going to deplete our 1024 buffer here. And 1024 minus 64 means there's only 960 instances left inside that buffer. So when TensorFlow sees that happen, it's going to go back to our training set, read another 64 images, refill that buffer, and then reshuffle it. So that's kind of like the additional explanation of what shuffle is doing. It's ensuring that that buffer is maintained and that data inside the buffer is randomly shuffled, which is obviously important when we're training neural networks. Nearly every data pipeline you create is going to end in this prefetch function, and it's also going to include the autotune. So prefetch is telling TensorFlow to not only build that initial data buffer of 1024, but we want to go through this entire process. So So TensorFlow under the hood is examining the auto tune. It's looking at your CPU. It's looking at your RAM utilization and saying, all right, how much data can I put into memory such that I run through every single one of these steps, such that the producer is creating as many cheeseburgers as he possibly can. That's what essentially this prefetch auto tune is doing. So the chef here looks over at the consumer and is like, wow, that guy's hungry. He could eat some cheeseburgers. So I'm gonna go back to the kitchen and I'm gonna take inventory of how many buns I have, how much lettuce I have, how much beef I have, how much cheese I have, and I'm just gonna divide my work up amongst the team and we're just gonna start creating as many cheeseburgers as our inventory will possibly allow us to create. That makes the consumer happy because anytime the consumer needs another cheeseburger, it's already been prepared for them. So keep that in mind and realize that anytime you create a data set pipeline, I mean, almost 100% of the time, you're gonna want to end it with this prefetch auto tune. And finally, we're ready to do our benchmark. So we're going to call our benchmark function. We're going to pass in the instance of our image data generator, and we're going to allow it to run for 5,000 steps. And we're going to benchmark how long that process took. And then similarly, we're going to create our data set generator from our data set itself. And we're going to benchmark that again for 5,000 steps. And finally, we'll be able to benchmark how long the TensorFlow Data API took to run. So all you got to do to run the script is come over here, copy and paste the usage, put it in our terminal, and you'll let the script run, and it'll generate all this data, and it'll give us the results for how long each of them took. So I have the output pulled up because I ran these results on the cloud instance, so I want to show you the original results that are included in the blog post. So we load the data set from disk, we create our image data generator object, we construct our TensorFlow data pipeline, and then we notice the output here. It took the image data generator class a total of 5.65 seconds to generate 320,000 batches of data. On the other hand, the TensorFlow Data API generated the same amount of data in 0.92 seconds. That's an incredible speed up. And that makes this producer consumer relationship so much more productive, so much more efficient. But what happens if you're working with data residing on disk? That is actually where the TensorFlow Data API really shines. It is even faster. And let's see how we do it. Opening up the reading from disk script, we have our benchmark function again. We have our image data generator class. We have our autotune magic parameter. We're using the imutils library and specifically the paths class here so that we can grab the paths to all images inside of our fruits data set. This is TensorFlow itself, NumPy for numerical array processing. We'll have argparse for command line arguments, and then OS for working with file paths in an operating system agnostic way. Now, this load images function, this is a really important function because what's going to end up happening here is we're going to grab the paths to every single image inside of here. And then we're going to create a data set from it. And the TensorFlow Data API is going to yield out the path to an input image. And we're going to be responsible for loading that image from disk and doing any pre-processing and scaling to it. So it is going to take significantly more code than using the image data generator class. And it's going to take a bit more knowledge of what's going on under the hood, but the results are going to be so much better. So let's take a look at this load images function. And again, note that it's requiring a single argument, which is the path to one single image on disk. So when we run this function, again, TensorFlow is going to know all the paths to images on disk already. So it can just run this function in parallel to run and load as many images at it as it sees fits. Notice here, before I explain what each of these lines of code is doing, I want you to notice that we're using TensorFlow functions, TensorFlow IO functions, TensorFlow functions for resizing images. Typically, we would use OpenCV for that, or Pill or Pillow. Why are we using TensorFlow functions here? It's because these functions, similar to how the data API has been optimized, these TensorFlow functions have also been optimized. And when you combine them together with the auto-tuning functionality, that's when you're really going to get your speed up. So when you start building these dataset pipelines, especially on disk, you'll want to start using the TensorFlow functions for reading and pre-processing images. It's going to be so much faster. Yeah, it's a little more tedious. You're going to have to spend a bit more time in the TensorFlow documentation, reading up on what certain functions do. And it's certainly going to take more code in order to build this. But again, the performance gains you're going to see makes it well worth. So here we load our input image from disk using the TensorFlow IO function read file. This results in an image. And we want to decode this raw image because it's just a byte array in memory right now. We'll decode it as a PNG file. Why PNG? Well, it's a lossless image file format for one. And this is just a standard function you would use for decoding a byte array. And since we're working with RGB images, we'll pass in that we have 3 channels. This line right here is doing 2 things. It's resizing our input images to a fixed 96 by 96 pixels, and we're also scaling the pixel intensities from the range 0 to 255 to 0 to 1, which is a pretty standard preprocessing and scaling technique that we do when training neural networks. So at this point, our image is ready, but we now need to parse the class label. We do that first by providing our image path, and then we're going to split that image path based off of the operating system's file separator, which is a / on Unix machines and a / on Windows machines. And the reason this works is because we'll be running this script from our root directory, and then each image path will be fruits / whatever the class label name is, in this case apple, and then apple01.jpg. So by splitting on the image path separator and selecting the second to last instance, that enables us to extract this subdirectory. And since our image file paths are organized in this manner, then we can just grab the name of the subdirectory, and that serves as our class label. But again, notice how I'm using tf.strings.split for this function. I'm not using Python's internal split function. It's again because we want to, whenever possible, when building these pipelines, you want to use TensorFlow's built-in functions for this. It's going to be super fast. It's going to allow TensorFlow to perform better optimizations. Next, we'll do some one-hot encoding on this since we know the class names from here, which I'll explain in a second. And then we'll grab the integer encoded label and return a 2-tuple of the image and the encoded label to the calling function. Now let's learn how to put all these pieces together. We parse our command line arguments, and the only argument we need here is the data set, the path to the fruits data set residing on disk. We'll use a batch size of 64 during our benchmark, and then we're going to generate 1,000 steps of data. So that's 64,000 total images generated from disk. And then we're going to benchmark image data generator compared to the TensorFlow Data API. Here is the line of code that examines our fruits directory and grabs the paths to all images inside the respective subdirectories. And we extract the class names here by listing the contents of the dataset directory. So this will give us the 7 class labels associated with our labels. And that allows us to do our one-hot encoding up here. This is where we create our dataset instance from the TensorFlow Data API. Again, we're calling the from tensor slices function, but since we don't have the raw data loaded in disk already, what we do is we pass in the image paths. So that'll tell TensorFlow to initialize essentially an empty dataset just filled with the file paths themselves. The dataset will then be populated with the image data later inside this pipeline. So we start by creating our pipeline here. We'll create a buffer of 1024 images and ensure they're always shuffled and randomized inside that buffer. And here is where we're going to load our images themselves. We're going to call the map function, which tells TensorFlow to map each one of these image paths to the load image function. And then we're going to pass in our autotune parameter here to tell us how many parallel calls to load images that we're allowed to make. So TensorFlow is going to determine the number of parallel calls automatically. We don't have to tune that up ourselves. TensorFlow is going to optimize this procedure for us. So that means for each image path, if there's 1,000 images, then we're going to call load images 1,000 times, one for each image. And then TensorFlow is going to make that process parallel as it sees fit. So again, single image path comes here, we load the image from disk, do our pre-processing rescaling and whatever else we have to do, and then we'll maintain that buffer of images. We cache the process as necessary. We're going to repeat the process in the sense that if we wanted to restart from the beginning of the data set, like at the beginning of an epoch, that's what that repeat function is going to allow us to do. We use a batch size of 64, and then we're going to prefetch a certain amount of data that TensorFlow is going to define for us based off the auto-tune parameter, which again is going to satisfy this producer-consumer relationship. So again, that's a decent amount of code, right? Because not only did we have to create our load images function, but we also had to create an instance of a TensorFlow data class, and then we had to define the pipeline itself. When you compare that to this block of code here, you start to appreciate that yes, TensorFlow data is going to give you a faster throughput, but you're also going to have to spend a little bit more time writing your function calls, defining any data augmentation procedures, defining any scaling and preprocessing functions, and of course, defining the function that actually loads the data from disk in the first place. Compare that to image data generator, and the image data generator is almost just stupid simple, We create an instance, and then the rescale parameter tells us that we want to scale our pixel intensities from the range 0 to 255 to 0 to 1. And we call the flow from directory function, passing in the path to our input data set, which is our fruits directory right here. And then internally, we're going to resize each of those images to 96 by 96 pixels. We'll have a batch size of 64. This class mode equals categorical will automatically extract the class label given our subdirectory structure, and then we're using RGB images. So this is obviously much more simple than this much more complicated process of creating the pipeline and then defining our load images function. But let's see if it's worth it or not. So first thing, we'll benchmark our image data generator and show the results, and then we'll benchmark the TensorFlow Data API and show the results down here. So if I were to run this script, I grab the usage, paste it into my terminal, and then it would start the process of creating the image data generator object. It would benchmark that, and then it would benchmark the TensorFlow Data API as well. So this is going to take a little while to run, so I'm going to kill the script and show you the results from when I previously gathered the results. Here you see we load our image paths from disk, we create our tf.data pipeline, create our image data generator object, and you'll see that we generated 64,000 images in 250 seconds, so just shy of 5 minutes. Compare that to TensorFlow.data, 6.81 seconds. That is an incredible, incredible speed up, right? Like what's the actual improvement here? Let's look at this. Was it 6.81? So you're looking at almost a 38 times increase in just improved producer-consumer relationship by using the TensorFlow Data API. Such a better producer-consumer relationship. And if we're talking about a 38 times improvement, yeah, I'd say it's well worth the effort to write this load images function and then kind of create this more nuanced pipeline than using the flow from directory function. Yeah, it requires more code. At least initially, you're going to spend more time in the TensorFlow documentation, reading about these various functions and getting used to them and practicing getting your function calls in the correct order. So there is a bit more of a learning curve, but the TensorFlow Data API gives you such better nuanced control of what the pipeline is doing itself that it's well worth it to go about constructing your calls in this way. You just can't argue with the performance increases. It's well worth. So again, this tutorial just eased you into the TensorFlow Data API, and we really focused on comparing the performance of the TensorFlow Data API to Image Data Generator and made a really good case as to why you would want to go about this process. But we didn't actually train a neural network using tf.data. That is what we'll be discussing next week. I'll see you then.